The dates are not working. The timer and the dates are I love learning. I really love regarding this.
All right, please do quiz 8. I still have not closed quiz 7 if you want to do quiz 7, but the correct answer to quiz 7 or 7A, you can do either one. I'll take the max, is given in the lecture that was recorded yesterday and is now posted. So if you haven't seen it, you should go there and see it, at least for the answer, but possibly for also some exam answers and stuff. So, check it out. So the correct answer for today's quiz is G for Gerald, I think.
Just to be clear, there are only 2 questions.
Yes.
Okay.
All right. And while you're on Quarkus, please leave a review or something. I feel like an Uber driver asking for 5 stars, but so if you would, that would be great. Any feedback is appreciated. Wait, it's not projecting. If you want to leave feedback on how I'm able to use projectors, that's I know. Oh, I see. So I think there was talk about kind of extra recorded lectures. So what I'm gonna do is I'm gonna finish up hopefully everything that I really want to say in this course today. So there's not gonna be like a mandatory there's not going to be a mandatory lecture that you must watch, but I'm going to do like a few optional ones that I'll announce. So one this weekend, and then probably you're not going to show up next week, but like maybe next weekend or something in between exams, I'll do like a review session. But kind of as far as mandatory material, it's got to be just what's today. And that's it. No? All right. Hello, new people. The correct answer on the quiz is G for Gerald. All right. So what I want to do is I want to skip a few slides and just talk about the course in general, and then I'm going to catch up on what I am promising to do here. So what is ESC190 about? And like the reason I want to tell you is like in part you might like to know because that's kind of the philosophy on the exam as well. So the main thing I'm trying to achieve, and I hope I achieve to some extent with 190, is to improve people's general programming skills, right? So like programming languages come and go, although C has been a constant presence for 30, 40 years. But really it's about kind of problem solving ability. And hopefully even in the future, kind of as language models get better, it's still going to be the case that understanding the output of the language model, which is probably going to do most of the coding for you, is still important. And I think the only way to learn how to read code is to write code. So I hope that that stays with you. And, like if you look at past exams as well, like it's not really testing like, do you know the small detail of the C programming language? It's more about, can you solve problems using C? So we also learned about a few specifically, but widely applicable algorithms and data structures. So the important point, and I think I made that point before, is like most problems are really difficult and there's no kind of straightforward solution to them. There is like a thin slice of things that humanity has figured out how to do. With some things, we went into a lot of depth. We built like we built spaceships and stuff. I don't know if I should claim the credit for that, but some people did. And we also invented dynamic programming and stuff. Maybe not an achievement on the same scale, but still. But we haven't invented a way to go to like other stars. There's like lots of things that you could imagine computers could do that we don't know how to make them do yet, although we're progressing. Still, it's important to know what's been achieved. So for example, we figured out how to do sorting fast. We figured out how to do some kind of optimization problems that are amenable to dynamic programming. We have figured out how to make data structures that let you access data quickly in some contexts. We'll do actually like 2 more today. So for example, people figured out how to do a priority queue in a way that's going to be reasonably fast. And because people figured out how to do a priority queue that can work reasonably fast, you can do stuff like A* from yesterday and so on, right? 3 reasons that we're doing those algorithms. Well, first of all, everyone does it, so like you have to. But second of all, it gives you an idea of the kinds of things that are possible to come up with. It gives you an idea for here's like the kind of thing that's possible to do if you think really hard. And also the algorithms we selected are actually mostly the algorithms that you would need in order to implement kind of subsets of Python, right? So basically it gives you an idea of how modern computers work because like mostly people write, Python or Java, and it's kind of the data structures that we learned about are basically underlying everything in there. And hopefully it's also transferable to just solving problems in general. So what I consider to be a good question on the exam that tests this is not asking you to like implement exactly the thing that we did in lecture. That doesn't really make a lot of sense. And I think you'll find very few past exam questions that are like that. So what I'm trying to do is like, here's an algorithm from lecture, or here's the kind of thing that we did for the project, which usually would not be like a widely known algorithm. And here's a spin on it that's a little bit different, but that kind of you can do if you know what the spirit of the solution was to the original problem. So an example would be the midterm question that was kind of like the project 1 problem, but simplified so that you could do it on the midterm. So that's the kind of thing that I'm looking for to test kind of, did you understand the spirit of the way we solve the problem? And the way to study for that is, to know how to implement the stuff that we did in lecture, the stuff that we did in labs, the stuff that we did in the projects from scratch or almost from scratch. Again, kind of to state the obvious, nobody can write code on paper that's going to even compile, probably. Like very few exam solutions actually compile to the longer problems. And of course, like, you know, you don't have a compiler, you miss a semicolon, nothing compiles. That's, you know, that's just how it is. At the same time, I feel like if you kind of implement something from scratch, even if you sometimes peek at the solution or at a solution, and you convince yourself that, okay, I could do it from scratch now, I think that's a good way to prepare for the exam. Again, there was a whole lecture about kind of catching up after the midterm and preparing for the exam, so you can review that. So the third thing that I hope we made progress on is understanding how the C programming language works, right? So important both for itself, again, kind of to just understand how the world works, also important for programming in C in the future, if that's what you happen to do, and for preparing for the hardware course, ESC252, I guess, next year. So what do I mean by how the C programming language works? So the answer is like, well, it's basically Python, plus you need to understand the pointer drills, right? So that is how I would approach studying for the exam as well. Like you need to do the pointer drills, and you need to kind of convince yourself that you understand all of that, ideally. All right. So I have just like one slide, and we'll skip back to the material right after this, but I want to make sure that I've said this. So in terms of looking ahead and progressing to, you know, like progressing more in your career if you choose to do something that's computing related. So the first thing I would say is there's like absolutely no substitute for working on your own projects, both in terms of learning and in terms of kind of getting opportunities. And I think kind of all of us kind of know this, but I think all of us kind of forget this because we're in this university framework where we have kind of courses and exams and stuff. But, you know, like if you do anything that's difficult, like if you play an instrument, if you play a sport, if you program, you know that like it's not about like, okay, like we have a curriculum and we just do the curriculum and then we prepare for the exam and then we can forget it the night after and it's all okay, I've learned it. That's not how it works, right? The only way to learn how to do hard substantive things is to actually do them. And also, like the best evidence, if you're looking at it from the employer point of view, the best evidence that someone is going to be able to work on a project that takes, you know, possibly months is to see if they've done it before, right? So for that reason, kind of the extremely common advice if people are looking for jobs in software is, you know, work on side projects and have something unique that you yourself built, that you were excited about, that that you actually made over a period of time. So the other thing, and this is like a bit of an unfortunate reality in terms of getting jobs, but that's just how it is right now, is, you know, like if you want to get the good jobs, most likely you need to practice just standard interview type questions. And some of it we started doing in 190. There's absolutely no way I could prepare you in 190 for PY interviews during the fall of third year. That's not a realistic goal. A goal that I have is that you should be able to start practicing. So that you do well in interviews in third year, again, if you choose to go into computing, but you know, most ANCSIs do in some fashion, right? So the standard book is called Cracking the Coding Interview. You can check it out. It has like 300 something questions, I think. Some of them are now. I think kind of the lead code style questions are still not out of fashion. Lead code is, of course, right there on the internet, and it has lots more problems. So as relates to this course, so we've done some dynamic programming, and we've done some stuff that's kind of like the easy problems on lead code. Dynamic programming, I think mostly is categorized as medium. I think like some of them are categorized as hard, some is easy. There is a grading on lead code. I'm not sure I always agree with the grading on lead code, just like some people decided. Check it out. So like I would kind of both as preparation for the exam. Some of those questions can be pretty good. And also in general, like if you want to get kind of the really kind of high-end jobs, then you got to do it. It's unfortunate because in a way, like it's just like a ritual that you go through where you practice those problems with honestly limited real world applicability. Sometimes like the point of having done those problems is that you've done them. It's not that you've made something new or anything. But that's the reality. And if you want to get kind of a high-end job, you should probably do it. That's kind of what I have to say. So again, we had the whole lecture about preparing for the exam. I don't really have more to say other than the lecture from a few weeks ago. That was like one of the Sundays when I was on the West Coast. Okay, so new people, the correct answer in the quiz is G for Gerald. Go do the quiz. Also, while you're in Quercus, leave a review or something. Okay. So I want to talk briefly about two data structures, and we'll try to make it kind of light. We'll see if it works out. So the first data structure that I want to talk about is called binary search trees, and it could be used to implement a dictionary as well, but we'll talk about it in terms of the set abstract data structure, right? So a set, you can insert into it, you can remove an element from it, and you can check whether the element is in the set. You could imagine kind of other operations like whatever intersection of sets, whatever, but really like intersection, for example, you would just like repeatedly check if like the element from set A is in set B as well, right? So that's kind of the minimal thing. So one way to implement a set is you can just do an array, right? So I hopefully don't need to put it on the slide, and I didn't, but if you do an array, you could. And then what would the lookup time be for an element in an array? Yeah.
Lookup would be O of n.
Yeah, so lookup would be O of n because like you want to know whether the element is in the set. Well, you got to check whether the new element is equal to possibly every element in the list. That's O of n. Right? Insert, well, depending on how you do it, could be O of 1, but if insert is O of 1, then delete is O of n, and vice versa, stuff like that. Right? Delete actually is going to be O of n either way. So here is a way to make it so that lookup is O of log n in some sense. We arrange the elements. So here, the elements of the set are integers, and we arrange them into what we call a binary search tree. So a tree, again, you have a root, and it's binary. That means that each node has at most two children. And the additional rule for binary search tree is that all the left descendants are smaller than the root node, and all the right descendants are larger than the root node. So here you see, like, to the left of 8 is everything that's smaller than 8. To the right of 8 is interesting. To the right of 8 is everything that's larger. So similarly, this works for subtrees as well, right? So 1 is smaller than 3, and then everything that's to the right of 3 is larger than 3. Okay, so that's different from the heap order, right? So heap order was just that the parent is smaller than the children. Here it's the left descendants, so the entire left subtree is smaller than the root, the entire right subtree is larger than the root. Okay, so it's another rule about how you're supposed to arrange the elements. And the reason they're arranged that way is that that makes lookup easy. So how do you look something up? So check whether 4 is in the tree or not. Well, I start at the root and I ask, okay, like is 4 larger or smaller? 4 is smaller, so therefore 4 is somewhere here. And then I ask, okay, like is 4 larger or smaller than 3? It's larger, so therefore 4 is somewhere here. And then I ask, is 4 smaller or larger than 6? It's smaller, so I look on the left and there is 4. Make sense? So that's the idea. What's the complexity of this? Well, we have as many steps in this process as we have nodes in the largest possible path. So the largest possible path from the top to bottom, that's the height of the tree, right? So how many levels? Does that make sense? Because like every time you go down 1 level. So how many levels do we have? So like we saw last week, if the tree is complete, then the number of nodes in the tree is 2 to the h minus, well, like approximately 2 to the h minus 1, where h is the height. Does that, is everyone good with this? Questions? All right. Are people complaining on Discord that I'm not sharing again? Nope. Okay. Maybe I am sharing. Okay. So that means that if the tree is complete, then you take all of log n steps because h is approximately 2 to the n. So O of h is O of log n. Does that make sense? Where n is the number of nodes in the tree. Is that making sense? Questions? Okay. Yeah.
Do we not have the 4 on the left branch of the 10?
Say again?
Do we not have the 4 on the left branch of the 10?
No. So the rule is not that just the children are smaller. The rule is like everything to the left of 8 is smaller, everything to the right of 8 is larger. Okay. So, all right. So that's if the tree is complete. The tree doesn't have to be complete at all, right? So this is a binary search tree, happens to be not complete. Like it follows the rule, everything to the right of 1 is larger than 1, and everything to the right of 2 is larger than 2. But it's basically a linked list, right? So the height of this kind of like very incomplete binary search tree is just n, approximately, the number of nodes. So in order to look up 3, you would have to go through all the nodes. So that would be all of that. So in the worst case for a valid BSD, the lookup is still actually all of log n. So, and you don't know what kind of favor I'm doing you, not doing the details of this. They're extremely annoying, but you can make lookup the all of log n in the worst case. So what that would involve is building the tree in such a way that it's almost complete. It doesn't have to be like completely complete, but like almost complete. And then messing with it every time you insert or delete so that it keeps being mostly complete. And you can imagine kind of doing that, right? So like if the tree is like almost complete, and then let's say that you, whatever, like you remove the 13 and 14 and then it's really imbalanced. Well, you can like move stuff around so that it becomes balanced. And as it turns out, there are quite annoying and finicky algorithms that are nevertheless fast that kind of rearrange the elements a little bit so that the tree keeps being balanced if you remove a node. Okay, so it's possible to do. If your data is static, then you could just arrange it in a complete binary search tree. And then if you don't need to insert or delete, like that's there, you don't need to change anything. So in that case, it would be all of log n. Does that make sense? Yeah.
So yeah, it seems quite difficult to like insert, delete, and organize.
I mean, it's not so much difficult as annoying.
Are those not like related or quirky?
What?
Are difficulty and annoyingness not
Are difficulty and annoying? I mean, I would say they're related, but some things are difficult but not annoying. Some things are annoying but not difficult in my experience, in life in general. And I mean, wouldn't it be unfortunate if everything difficult was also annoying? Like anxiety is not annoying, right? It's just like a lot of things, but not that. Yeah, I mean, I let's defer this discussion. I agree that those are not entirely unrelated. Anyway, you can look up AVL trees and red-black trees and make your own judgment about whether it's difficult and or annoying. So I would say a prime example of annoying but not difficult. All right. So let's look at the implementation of this. So again, this is in the slides. I'm just copy and pasting. So what I'm doing here is making a tree that's kind of linked list style, right? So I'm defining a node like that. So a node will have possibly a left child that's going to be none if there is no left child, and it's going to have a right, and it's going to have a value. All right. And then here I'm just making this sample binary search tree where the root is, she changed it around. So the root is 3, and then to the right of 3 is 1, and then to the left of 1 is 0, to the right of 1 is 2, and to the right of 3 is 5. Does that make sense? I shall paste it back into the slides so that it's correct. Is that good with everyone? Questions? So it's in the slides as well. You don't need to type. So now what I want to do, so now that I've built this, I want to do search. So return true if the key is in the tree with root. All right. So you can do it either recursively or iteratively. Recursively, to my mind, is actually easier in this case. So what do we need to do? Let's say that we're looking for 4. So 3 situations. So if we're here, either 4 is just equal to the root, and then the answer is yes, it's there, we found it. Or 4 is potentially on the left, or 4 is potentially on the right. So if 4 is greater than the root, then it's potentially in here. If we're looking for, let's say, 2, then if it's there, it's on the left. So the base case is going to be 2 base cases, actually. So if the root is already none, so if we got to an empty tree, then key is definitely not there, the tree is empty. If the value of the root is equal to the key, then we found the key. So the answer is yes. And now the situation is, well, like that is bad, by the way. So the situation now is either the key is on the left or the key is on the right. So if the key is smaller than root value, then if it's there, then it's in root dot left, right? So if it's there, it's in the tree that starts here. If it's not there, then it's also not in the left tree. It's definitely not in the right tree. So therefore, whatever the search for the subtree that is rooted at 1 returns, that's the correct answer. Does that make sense? So if we're looking for 2, for example, then either 2 is not there or it's in here on the left. So whatever search for the tree that's rooted at 1 returns, that's the answer. And that's what we're saying here. Is that making sense? Questions? So the other possibility is that it's not equal, it's not smaller, so it's greater. So whatever search returns for root.right is the correct answer. And that's it. Yeah.
We're starting from the top.
We are starting from it. Yeah. So like people sometimes draw trees like the way they grow, which is like the opposite way. But yes, like we are thinking about it as at the top.
How can it see?
Yeah. Right. So we're saying, is the key smaller than the root? If it's smaller, then look in the left subtree. If it's larger, look in the right subtree. If it's equal, you already found it. Those are the 3 options, and that's the entire algorithm. So this is one of those situations where recursion is like a really suitable technique, because yeah, like you just look in the left and it's a subtree, look in the right and it's a subtree, and you need to search in either the left subtree or the right subtree. Make sense? Okay, so that is what I have to say about binary search trees. Again, like if it has to be dynamic, so if you need to add and remove values, then this is actually not enough, because you need to know how to arrange the tree so that it's actually a binary, it's actually a balanced binary search tree. And like I said, it's like not something that we're going to do in this course, although you could. But that's the search algorithm. And if the tree is balanced, then you get O of log n access time. Yeah.
Are there some like common applications of this?
Yes. Like if you want to implement a set. Yeah. So so in Python, we're going to talk about how like the usual way that sets and dictionaries are implemented in Python, which is hash tables, which I think we'll have time for. In Java, this is like the default way to do sets. So, and again, kind of sets and like a dictionary, you can also think about it as a database. So maybe it's not obvious, but so we are talking about dictionary, about sets, but a dictionary is like something that's very similar, right? So essentially all you need to do is attach some kind of data to, that's why they're called keys, to every key, right? So for the set, you just have like an extra pointer that's the data in addition to the key. The key, yeah. Does that make sense? Yeah.
For our search function, it said that the worst case runtime complexity is O of log n.
So if the tree is complete, it's O of log n. In general, it's O of n. Does that make sense? So if it's complete, then it's O of log n, because it's like arranged in a special way. In general, it wouldn't be arranged in a special way. It could still be a binary search tree like this one. And in this case, well, to get to 3, you need to go through all the nodes. There's n nodes, that's O of n. All right, last topic. So we're going to do a little bit of hash tables. Again, I'm going to skip some of the implementation details that are maybe not essential. The ADT that corresponds to Python dictionaries is called a map in general. That's just what people say. So in Python, people chose to call it a dictionary. A map is a dictionary. That's just what people call it when talking about it in the context of abstract data types. So how do they work? Well, they work the way dictionaries work. So there are key value pairs. The keys must be unique. The values do not have to be unique. Right, so it can look kind of like this, where key 3 and key 4 happen to correspond to the same value, but the keys are unique. Right, so this is not anything weird. This is just a Python dictionary. Does that make sense? I guess a Python dictionary where it happens that D at key 3 and D at key 4 are like aliases. So, okay. So what can you do? Well, one thing you can do is if you happen to have a set ADT already implemented, just stick the value together with the key and you have your dictionary. Right? Does that make sense? So like you look up using the key, and then in each node, in addition to the key, you also store some other stuff, right? So here we just said self.value equals key. You could also have like self.data equals whatever. And that's the entire, and then you send the data as well. That's the only modification that you need. Is that making sense? So you look up using the key, but you also happen to store the data in each node. Okay. So you can do that. And again, we haven't actually implemented AVL trees. So we've implemented a simple BST, which is worst case O of n, which is slow. But you could do O of log n if you try again. So you can use an array of values, right? So if your keys are just integers, just use an array. That's of one, both get and put. What's the problem with this? Well, it says on the slide, if your keys are integers, but they can be extremely large integers, then you need a huge array, because you need to pre-allocate the array with all the possible indices that you could have. And if all your possible indices that you could have are like anything goes, then it would need to be a huge array. So that might not be practicable, but that could work. So if you remember, counting sort kind of works in the same spirit, right? So if you have a restricted set of values that you could take on, then you could just use an array and you have all one axis. Does that make sense? Or you could use hash tables and get around the fact that arrays are fast but extremely large. So here's how that could work. Yeah.
We have, you just told us we have 3 options to implement.
At least 3. Yes.
Basically 3, and that's just adding a value to our BST using an array of integers.
Well, like if you have set implemented, however you have the set implemented, you can just augment it with also storing the value. So like any way that you implement a set would work for a dictionary. Does that make sense? Yeah, you can do a tuple. Well, so like if you do it as a tuple, so you could. So here it's not exactly as a tuple in the sense that I'm still using the value in my search, right? But sorry, the key in my search, but I also have the data, right?
That's the binary search tree.
Anything, or like anything that you can store keys in, you can also just stick data.
So like that's what you're talking about, right?
Yeah. No, so the array is different, right? So the idea with the array is if I have integer keys that are permitted, I could just say a key is an index in the array. So I'll allocate the array, and then, if I want to look up the value at index 1,050,000, I'll look at index 1,050,000.
There's something like zeros in between, so like nulls in between. So
You could, yeah. In fact, the problem is that you have to, right? So you have to put something. You have to put something there, because if you try to get away with just storing the values, first of all, you don't know where your values are, so you cannot look them up and know of one time. Well, that's the big problem. All right. Is that making sense to everyone? All right. So here's the idea for hash table. So let's say that we want to store like names and phone numbers. So we want to store a phone number for every name. So we'll have a table, meaning an array. And then we'll have a function that converts the key into an index. So that's what's called a hash function, right? So all I'm saying is we'll have an array, and then we'll have a function that will take the string Alice, and it will tell me, oh, like Alice is cell number 1. Make sense? Yeah, and not the Alice was here, a general Alice. So okay. So do we have a Bob as well? I don't know. Anyway, so okay, so and the idea would be kind of Bob would be mapped to a different location in the table. So how do you make a function like that? So let's say that we want to
integers, is that just based on like in what order they're added to the
no, guilty. Yeah. I mean, in a way, in one of the flavors, yes, but no. So what can we do? So one thing I could do, so let's say that we have, whatever, Charlie, and we want to convert it to an integer. Well, Charlie is a sequence of letters which we can convert into numbers. So something like this. And if you remember, in Python, you can do ORC to get the ASCII value of a letter. And now we want to map it to some number that's going to be different for different different characters. So one thing you can do is just make like a very large number. So you can do like 67 times 10 to the power of 10. Well, let's do 6 plus 104 times 10 to the 4 plus 97 times 10 to the 3, and so on. So that's going to be a large number, and that number is going to depend on exactly what the characters are. So the inspiration for this is that if those were digits, then basically we could convert this into a number like this, right? So that would be just whatever, 1, 2, 3, 4, 2. So that's kind of the vague inspiration, is like, well, like if those are different digits, you'll get different numbers every time. So you also want for this to be a number between 0 and n-1, which for most n's, this is not going to be. It's going to be much larger. But if you do mod n, that's going to give you an index between 0 and n-1.
N is the number of letters.
the number of cells in the table. Right. So what we want to do is we want to take Bob and we want to know where Bob's number is. Right. So so we have our table size and we want to index so here between 0 and table size -1. So we make this huge number based on the contents of the name. And then we just do mod table size to get an index between 0 and table size -1. So the idea here is, so like the idea of hash, it's kind of like that it means like you have like a pile of stuff and you want to like pinpoint the location of your particular thing. Right. And that kind of does it, right? So like you change a letter, you get a different index. Yeah.
How do we do this though with N's like changing? We have a
We'll get to this. Yeah. Or maybe not.
You have table that's kind of like change a variable to like it changes the variable of the string.
Yeah, you could think of it. You can think of it that way. Yeah. Yeah. That's good. Yeah. So that's the idea. So assuming that you can have a hash, assuming that you can have a hash table, a hash function, sorry, like this, which takes in the key and figures out the location, you're done. So now this could be just an array, and the hash function figures out where in the array is your data for any particular key. So if hash of key is of 1, and if you have 1 element per cell, then that's it. You have of 1 insert, of 1 lookup. Yeah. Well, yeah. So the size. So basically, if your hash function is kind of reasonable and you're not super unlucky, you won't have what's called collision. So a collision is when 2 different keys are mapped to the same location in the table. Right? But if you keep inserting, eventually there's definitely going to be a collision. So in particular, if you try to insert more than table size elements, there is no way that there's not going to be a collision. So there are various ways of solving this. So yeah.
What do we define table size?
Table size is we define it as table. Well, whatever you want to call it. Yeah, the size of the table. Yeah. So like in the code, it was n. Okay. So if you have a collision, one thing that you can do is to just have a linked list. So if both Anna and Alice were mapped to index 1, just have a linked list. So the last thing I'm going to say here is that if you do it, you've broken the O1 worst case guarantee. And that's because potentially everything collides and all of your elements are just chained in one big linked list. So your worst case lookup is again O of n because you have to go through the linked list to find the element. That is what happens. So that is what happens with any style of hash table, including Python dictionaries. That is why, and if you remember, I think you asked me like about a question that was related to that. Like, I forget the question exactly, but the answer was it's all linked list underneath. So a hash table in general, if it's not too full, it's going to be O of 1. If it becomes full, then collisions become more likely. And in the worst case, either way, it could be that you are unlucky and all your keys map to the same hash index. And you think you have a hash table, but really you have a hash table with one big O linked list. Yes.
Does Python by default just say like, let's let n equal 1,000? Doesn't go above that, or like, what is it?
Well, so in general, yeah. So that was the question before. So yes, you start out with some size of a hash table, and then if it becomes too full, then you just expand it.
rather than like just increasing. Because it seems like, I guess then you could recompute all.
Yeah, you would have to recompute. Yeah.
But if you-
So if you're, so it's kind of the same if you remember the circular array representation where, yeah, like if you needed to expand, you needed to copy everything over.
Yeah.
That is all we have time for in this course. Again, while you're in Quercus, why not fill out an evaluation? And I will see you at the review sessions maybe. See ya. Bye. Thank you very much.
There's actually like no way around this. It's not like there's a lane thing. There's just a